Imagine walking down a busy city street when suddenly, hundreds of feet above, a sheet of glass silently releases from its frame and plummets toward you. This isn't a scene from a disaster movie, it's a recurring reality in cities worldwide, from Boston to Austin to Shanghai. The question haunts every facade engineer: why does skyscraper glass fall? And how do we stop it? Let's uncover the hidden science behind these terrifying failures. The most infamous culprit is something you can't see with the naked eye: nickel sulfide inclusions, or NIS stones. During the float glass manufacturing process, tiny particles of nickel and sulfur can become trapped in the glass. In annealed or heat-strengthened glass, these inclusions are harmless, but in tempered glass, which is rapidly heated and then quenched to create surface compression, the story changes dramatically. The rapid cooling traps these NIS particles in a compressed state. Over time, perhaps years later, they slowly expand back to their original size. If this expansion happens in the central tension zone of the tempered glass, the force can overcome the glass's internal stress, triggering an instantaneous, catastrophic shatter that sounds like an explosion. The characteristic butterfly-shaped fracture pattern at the break's origin is the forensic signature of nickel sulfide failure. But NIS isn't the only villain. Edge damage is actually the most common cause of seemingly spontaneous breakage. Glass is strongest when its edges are pristine, but microscopic chips or nicks during cutting, transportation, or installation create stress concentration points over months or years as the building sways in the wind. As temperatures cycle day to night, these tiny imperfections grow until the glass finally gives way. A pro tip from facade contractors: handle every panel as if it's already installed, and inspect edges under bright light before acceptance. Once installed, you can't fix what you didn't see. Then there's thermal stress, a silent killer that designers must anticipate. When sunlight strikes a glass panel, the center heats up and expands while the edges, shaded by the frame, remain cooler. This temperature difference creates tensile stress at the edges. If that stress exceeds the glass's edge strength, breakage occurs. This is particularly dangerous with insulating glass units that have solar control coatings. The coatings manage solar heat gain but can exacerbate temperature differentials. The solution lies in proper thermal stress analysis during design, especially for large panels with high-performance coatings. Installation errors also claim countless panels: missing setting blocks, improper gasket fit, or frames that don't accommodate building movement. All create point loads where glass meets metal. When the building sways or expands, that contact point becomes a stress raiser. I've seen projects where installers forgot to use edge blocks entirely, and within months, corner breakage appeared at the exact spots where glass rubbed against aluminum. Let's not forget the wind, specifically what researchers call building cluster wind effects, or in dense urban canyons like Shanghai's Lujiazui or Chicago's Loop. Winds accelerate and swirl unpredictably between towers. These localized gusts can far exceed design assumptions, creating dynamic pressures that fatigue glass and frames over time. The famous John Hancock Tower in Boston lost over 2,000 glass panels during construction, a disaster ultimately attributed to insufficient structural stiffness, combined with wind-induced oscillations that literally twisted the building. So what's the solution? First, specify heat-soaked tempered glass for critical applications. This process exposes glass to elevated temperatures to trigger early failure of NIS-contaminated panels in the factory, not on the building. Second, for overhead glazing or locations above public areas, mandate laminated glass. Even if it breaks, the inner layer holds the fragments in place, preventing dangerous fallout. Third, rigorous quality control during fabrication and installation catches edge damage before it becomes a catastrophe. And finally, facade inspections shouldn't stop at construction. Regular maintenance cycles catch early signs of distress before panels release. The truth is, glass doesn't just fall for no reason. Every failure has a root cause: a microscopic inclusion, a missed edge chip, a thermal calculation that didn't account for today's larger panels. By understanding these mechanisms, we don't just build taller, we build safer.